Okay, so it's time, so let's get started. Thank you everyone for tuning in to another Online Risk Institute seminar series. So today we have, just try again. So today we have Professor Christian Schilling from Aalborg University, who is going to give us a talk about a gentle introduction to reachability analysis for dynamical systems. But before we get started, let me promote the next week's talk by Mr. David Ropek. This is going to be the next week, 19th of July, it's 3 p.m. The talk is on the risk communication is not just about facts. So looking forward to seeing you there again. And so now I'm going to give you some introduction about today's speaker, Professor Christian Schilling. So he receives his doctoral degree in computer science from the University of Freiburg, Germany in 2018. And he was a doctoral research fellow at IST Austria and an interim professor for cyber physical system at the University of Konstanz, Germany. Since 2021, he is an assistant professor in the Distributed, Embedded and Intelligent Systems group at Aalborg University in Denmark. Christian's research in the area of formal methods is focused on the analysis, verification and synthesis of systems with dynamical and machine learned components. If you could keep your microphones muted, the talk is going to be about 45 minutes, followed by this Q&A and discussion session for about 15 to 20 minutes. And now I'll pass to Christian whenever you're ready.
Yeah, thanks. I'll share my slides. Can you see them?
Yes, that's perfect.
Great. So thanks for the kind introduction and also thanks for the invitation. Yeah, as you said, this is going to be about reachability analysis. And my goal with this presentation is to give you a broad overview and of course heavily biased to what I worked on. But it's not supposed to be technical. Okay, so let's start. So first let me describe what I mean by a dynamical system. For me, this is a continuous time system, which is modeled by an ordinary differential equation or a system of ordinary differential equations. So the rate of the current state change is a function of the current state. And then you can define an initial value problem, which is just given an initial state, give me the solution or trajectory. In general, such a solution does not exist, or if it exists, it's not unique, but I will assume that we have nice systems where this solution exists and is unique. So let's start with a simple example, this harmonic oscillator. This can be used to model very simple periodic phenomena in the world. For instance, a frictionless spring where you have a mass attached, you put it down and then it will go up and down forever like this. Similarly, if you have a pendulum, you pull it to the side, let loose, then it will swing like this forever. And this is has a very simple mathematical description. Here, just a two-dimensional system with a linear differential equation. And you can, if you plot this, the first dimension over time, you see this, this periodic behavior. And if you plot the two variables against each other, then you see a perfect circle. So when I look at these differential equations, I don't make much sense of them. I need such a visualization at the bottom, which you usually get with a simulation from an ODE solver. And I will try to convince you that these simulations are not always perfect, because this is basically the number one tool used in, well, whenever you have differential equations to visualize them. But yeah, I think there are some problems. So the first problem is maybe a bit artificial. If you use an ODE solver naively, you have to also usually decide on a time step. So for instance, a simple Euler integration with here a time step of 0.5. Instead of giving you the circle, it will give you a trajectory that diverges. So you have these numerical issues with ODE solvers. But as I said, this is maybe a bit artificial because yeah, there has been a lot of research in ODE solving. I don't know much about that myself, but I think in practice, you don't see these problems. Still, if you really need very high precision, this is a, let's say, mild concern, but the other problems are more serious, I think. So the second problem is if you don't want to have the solution for a single initial condition, but for a whole set of them. So let's say we want a solution for this whole range between -1 and 1, where we can start with 1 and we can try with -1. So now we tried 2 simulations, but that's not enough. So let's try some uniform selection between those. This gives us typically a good idea, but what happens for the infinitely many points in between? We don't know. For these simple linear systems, it's actually sufficient to look at the borders. So if your initial condition is basically a polytope, you can start from the corners from them. But this is not the case for nonlinear systems. You could have some very isolated initial condition, which gives you some completely different behavior. So this is really, if you really want to be sure that you covered all your behaviors, this is really concerning. And together with the third and last problem, which is dimensionality. So if you have a one-dimensional system, then sampling is usually easy. So here you have an interval, and I sampled 100 points from it, and that gives you a good coverage. 100 points from a two-dimensional set is already quite sparse. But if you now have a 100-dimensional system, you can imagine that you would need a lot of simulations to really cover that space. If you remember, I told you that for linear systems, you could just start from the corners, but even a simple hyperrectangular initial conditions or rectangle in high dimensions would have 2 to the power of n vertices. So in 80 dimensions, you would have as many vertices as you have atoms in the universe. So this is not a way to go with simulations. So if you really want to know everything about your system, simulations are not safe. And this is where I think reachability analysis can give you a really nice tool. And now I will explain what this is about. Namely, you want to actually, instead of computing a single solution, you want to compute the whole set of solutions. Or since this is not possible in general, you want an enclosure of these solutions. So what I did here is I computed a set, this here in cyan, that covers all the behaviors of this system. You can see this as a set-based simulation because we, instead of starting from a single point, we start from a set, and then we compute what is reachable in forward time. It's also a proof method. So if you want to reason about, I will have a slide later on that. If you want to reason about the safety of a system, you can use this set that this method can compute, and then check if an unsafe condition is in that set or not. And last but not least, actually for certain classes of systems, this is really fast. So for linear systems, for instance, you can run this with thousands of dimensions. As I told you, with simulations, you would really come to a dead end very soon if you have high dimensions, because you will not be able to cover all of it. So here I also plot on top the simulations just to show you that this set that we computed here is really precise. So it's not really a large overestimate of the the states that can be reached. Yeah, here's a small detour about verification. So if you want to verify that the system is safe, that means you want to, starting from an initial condition, you want that your trajectories that come from this start here do not enter this set of error states here in red. So yeah, you can try the simulations and you can run that as long as you want, but you will never be sure that there is not one initial condition that you forgot. Instead, you can just say, okay, let's compute the whole set of reachable states. And then we just check intersection with these two sets. And if these sets are disjoint, you have a proof that there is no trajectory that enters the error states. Unfortunately, this question is undecidable. That means there is no algorithm that gives you a yes/no answer under all conditions. So either your algorithm will be incorrect or it will not terminate in some instances. But still, what you can do is you get an approximation of this set. So usually for the purpose of verification, you want an over-approximation here in this form of these yellow boxes. And if you can show that your over-approximation is disjoint from the red error states, then of course it follows that the true set that you cannot compute is also disjoint. So that's basically the idea that why reachability analysis tries to be conservative, over-approximate. An important restriction for this presentation is that I will only consider bounded time settings. So I will basically compute these yellow boxes until a certain time horizon. Yeah, there are approaches to handle unbounded time, but these are, I would say, more complex. Okay, before we go into the into the different topics, here's some advertisement about our tool called JuliaReach. This is written in the programming language Julia, hence the name. And I co-developed this mainly with my colleague Marcelo. And yeah, so we are developing this tool now for I think 5 years, and we have also won several prizes in friendly competitions of such reachability tools. Here's some small teaser of what we can achieve. These are different model problems, whatever, with different dimensions. So here we have a 48-dimensional system. These are linear systems, by the way. The 200-dimensional system. Here, these are lower dimensional, but they have other complexities. For instance, these are hybrid. We will come to that later. Here, some results for nonlinear systems. Of course, I selected those results where we are very good. But I think in general, our tool is quite at the state of the art. Okay, so now I will talk a bit about nonlinear systems, and I start with some impressions of what you can achieve. So this is the van der Pol oscillator with 2 different parameters, and then this gives you these different shapes in red or blue. This model has the property that it has a limit cycle. That means all the behaviors in the neighborhood are basically pulled in to this shape that you see here. And you can see here the behavior starts here and then goes around. Oops. And then it enters here again with a smaller set. And that means you can actually prove that it converges. And in this case, we can even have an unbounded time proof, because we find that we are in a region where we have already been before. And so we have a loop. This is the Lorentz system. This is quite famous for having chaotic behavior. So even for that, we can bound this behavior in some quite precise way. This is a quadrotor model. So many of our benchmarks come from engineering. In this case, the quadrotor is supposed to go, I think, 1 meter up. So from 0 to 1. It does that by going a bit more than 1 meter, and then it corrects, and then it reaches this height. This is another domain that is quite frequently seen in this area is biology or chemical reactions. Here you can see we can very nicely preserve this spiral shape. Yeah, and also this famous epidemic model. We can model initial uncertainties in the distribution of infected people and so on. So this is all nice. So, but there are also some problems, of course. So for nonlinear systems in general, or no, I should start with the first item. So what we do is is sometimes called reach tube construction. So if I go back, you compute these tubes, right? And they contain all the behaviors. And yeah, actually, if you look closer, you see that there's this tube consists of many vertical bars, basically. These are different sets. So you compute them one by one. And the problem is that this reachability problem, so whether a state is reachable, is undecidable again. So you cannot compute this true set. So you would either have to over or under approximate. I already talked about that. Usually we want to over approximate. But over approximation leads to a famous problem called the wrapping effect. So I will try to explain that. Here you have this green triangle, and if the dynamics have a certain property, then it actually preserves this triangular shape over time. So these are just 5 steps or 4 steps. But if you say you cannot deal with triangles, they are too complex for you, you instead can only work with boxes, then you would take a box of that triangle and propagate this box instead. Then you get this red diamond. Again, you cannot work with diamonds, so you take another box. You propagate this box, you get this other diamond, and you see the problem. In every iteration, you will accumulate your error from the previous step. And yeah, very quickly, your error is bigger than the actual set. What you want to achieve is some error-free, a wrapping-free algorithm. Here we can actually get the box. So we still cannot deal with these more complex shapes, but we can nicely approximate them with precise approximation. So in particular, we don't accumulate the errors. And for linear systems, you can achieve that. For nonlinear systems in general, you cannot. Before I continue, I want to quickly mention there are other approaches to reachability analysis than this reach tube construction. One is called invariant generation. Instead of computing the set forward in steps, instead you guess a set, and then you verify that this candidate is valid or not. This is completely different paradigm. And an alternative, or it's not actually an alternative, it's more like a way around, is to abstract your system. So if you have a complex system, you might be able to turn it into a simpler system, for which you can then use more efficient algorithms. Okay, so what can you do for nonlinear systems? What do we do? Let's say we use Taylor models. These are basically truncated infinite Taylor series. So after truncation, they are of course not infinite anymore. So you have this Taylor polynomial, and then you say at some order you stop, and you put you estimate the error, and you put it into an interval at the end. So like here. And then this Taylor model is valid for a certain domain. Typically, this is this -1, box. And then this seemingly innocent polynomial here, or 2 polynomials, they give you this rather complex shape. So these are quite expressive and help you to preserve the precision for nonlinear systems where really crazy things can happen. So if you were wondering how to plot this is actually a union of many small boxes, because it's actually already a challenge to plot these complex shapes. So how can you work with these Taylor models? You would actually wrap them into another polynomial where you introduce a new variable for time t, and then you, with some techniques, propagate this forward. So here you see a blue set, a purple set, and a green set for 3 steps forward. And just to give you an idea of how complex this becomes, this is the blue set. So here I used an order 8 approximation. So here you have terms with t to the 8. But of course, this is something that the computer does for us. But still, it gets nasty quite quickly. Another approach for nonlinear systems is to actually linearize them. I hinted at that with this approximation of a complex system by a less complex system. There is I think already about 100 years old technique called Kahleman linearization, which takes a polynomial system and gives you an infinite dimensional linear system. And then you can, of course, not work with an infinite system, but you can truncate again, and then you get an approximation, but there is no formal relationship between the approximate system and the original system. But then I think 2 years ago, some group of physicists found an error estimate for a certain class of systems. And then we used this formula to derive a reachability algorithm. So you can basically analyze this linear system for which there are very efficient algorithms, and then put this error estimate on top. And that's what you see here in this, for instance, this yellow part is the error estimate. So we don't know where exactly the nonlinear system has its behaviors, but it's somewhere in this union of green and yellow. This is a work in progress. I work on with, among others, with Ander Gray and Scott Thurston from the EU Institute. I don't want to say much. It's just we use p boxes to propagate through Taylor models, and we can treat then initial uncertainty, so some distributions over the initial states. Coming to linear systems, why do I want to talk about linear systems? Well, because they are really so much better in terms of support from the tool side. So here's a 10,000, almost 11,000 dimensional system, and I can get this reachable states in about 90 seconds. So this is really beyond anything you can do for nonlinear systems by far. The problem itself is, from the complexity point of view, is still undecidable, so not really easier, but in practice you can do a lot. Here's the basic idea of how all the tools for linear systems treat them. Let's say this is the initial condition. You can compute until a small time horizon well, you cannot, but this is just for visualization. These are some trajectories until some short time horizon. Then you will approximate this set. For instance, with this blue set, this doesn't look like a great approximation, but the good thing about linear systems is that you can then just take this set that you computed and in a discrete way, so you turn this system from a continuous system into a discrete system, and then you can just propagate this blue set forward. And this is very efficient, especially if you use specialized representations for these sets. And as you can see, this is really, if you instead computed the exact trajectories, they would still stay inside. And of course, there's a proof that this is the case. So this is safe to do. And that's why you can you don't lose any precision. You have this wrapping free property, and it's very fast to do this propagation because you're actually not working with a continuous system at all anymore. So just to basically hand-wavily prove that this is the case, here's this harmonic oscillator from before after 500 periods, and you see there's still no sign of an approximation error. And you can compute this. So these are 300,000 steps, and you can compute this in less than a second. So this is really super efficient. I'm looking at the time. I think I have time for that. So this is a short view at an algorithm that we developed to make this analysis of linear systems very fast. So the usual analysis goes like this. You compute this, let's say this approximation here in yellow, and then you propagate this yellow approximation forward. What we do instead in this algorithm is we first decompose this set. So in this case, it's a 2D set, right? For plotting, I need to use 2D. So I need to go down. So what I want to do is I want to split the dimensions into lower dimensional subspaces. But in 2D, I don't have many choices. I have to go down to 1D, which looks really maybe very coarse. But in general, I don't need to do this. Just for the illustration, I need to do this. So I get this red and blue interval such that the Cartesian product of these intervals gives me this blue box, which is obviously an outer approximation of this yellow set. Then for the next step, I could now propagate this blue set and get this blue set, but this wouldn't help us because it would be the same computation as for the yellow set. So I wouldn't gain any speed, but I would have lost precision. That would be a lose-lose situation. Instead, we will do something. I will just briefly go through this, and you don't need to understand this expression here. So if the system matrix is decomposed by this decomposition into this block matrix here, we can evaluate this expression, and then we get this red interval here. And we can do the same in the other dimension, and then we get this blue interval. And then this Cartesian product is this purple shape. And yeah, obviously this is also an outer approximation. So what did we gain? So at first, what did we lose? We lost even more precision. So this looks really very coarse, I know. But the good thing is that we still have this wrapping free property. So in the next step, your error will not accumulate. So you will have more error, but it will stay in that region. What did we gain? We actually, this expression is more efficient to evaluate. So even if you do this, you want to compute this purple box, it's more efficient to do that. But what is really the main benefit is that the computation for this interval is completely decoupled from the computation of this interval, which means that if you are only interested in a property in x1, you can completely forget about the dimension x2. And in 2 dimensions, well, you save 50% of the work, which is already great. But if you have a 100-dimensional system and you're only interested in 1 dimension, then you save 99% of the work. And that's how we can really deal with these 1,000-dimensional systems in an efficient way, because we basically can skip most of the work. Okay. In the last part of the presentation, I want to talk about some extension, let's say, of these dynamical systems with discrete behavior. So a famous model for that is called a hybrid automaton. So you have these modes, which each of them have their own differential equations. So this would be something, for instance, here in this example, it's a thermostat controller, where if the thermostat is on, then, let's say this is more a heater. So if the heater is on, then it will heat up the room. And if it's off, then the temperature in the room will drop. So these are really very distinct behaviors. Then you have something called an invariant, which is the condition to stay in this mode. And then you have these transitions, which also have a condition called a guard. So whenever the temperature is between 22 and 23 degrees, the heater can switch off. And actually, if it's 23 degrees, then it has to switch off. And likewise, between 17 and 80 degrees, it would switch on again. So then you can get a behavior like this. So somewhere in this region, the heater would switch off, and then here it would switch on again, and so on. These systems are more complex to analyze. Here's basically what you do. So this is, let's say we are in one mode with this invariant. You do these computations of these reach tubes as before. So you compute this sequence of sets, and then you check intersection of this sequence with the guard condition, which is this big triangle here. And then you do you take this jump to this transition. Sometimes there's even a change of state action associated with these transitions. We didn't see that on the slide before. And then you basically play the same game from there again. So you need these 3 additional steps. You need intersection with invariant and guard, and then also apply this update. But the problem is that these set representations that behave nicely in this reach tube computation, they are not so great for these other operations. So that's why the scalability is a lot different. For such systems, we also extended our decomposition approach. The insight was that if your guard condition only talks about low dimensions, so let me go back. So if this condition to jump to a different mode, here in this case, it talks about one variable. Let's say you have a 100-dimensional or a 1,000-dimensional system, but you're only interested in one dimension, then this sounds like a use case for our decomposition algorithm that I showed before. So what we will do instead, we will first run this analysis in low dimensions to determine those sets that will take the jump. And then later we only compute the high dimensional sets for those, because we need the high dimensional sets to actually do the jump. But we can save the time for the other sets. Okay, and in the last section, I want to talk about control systems, because these are basically the main applications of these hybrid systems. So you have a digital controller for a dynamical system to do whatever you want to do. Here we have an electromechanical brake. This has a very simple time-triggered event. So you have a time, this variable t evolves with time, just like a clock. And whenever the time is between around the value tau, but with some uncertainty of size iota, then you take this transition. So you can think about it, it's a periodic controller where, let's say every second it fires, but there is some small uncertainty that it might be, I don't know, a few nanoseconds after 1 second or before 1 second. And for such a structure, we designed an algorithm that is much more efficient. So we can, it pays off once you have a lot of transitions, because usually if you take these many transitions, you either lose precision or you lose speed. And if you are careful about and exploit the structure of such models, you can avoid that. So we can analyze such a model in 9 seconds, where a previous work would use 13 hours. Then we have lately we see these learned components in cyber physical systems, especially neural networks. they work surprisingly well in many cases. But the question is, do they always work, or is it just in the simulations that we see that they work? So this is a general control cycle. You have this dynamical system here, or plant, and then you have a sampler. So let's say every second you let the controller sample your state, and then it will give you a control input. Let's say go left or right, or whatever the system is about. So what if this controller is implemented by a neural network? You can, I don't want to go into the details, but there are techniques to actually take the set that we computed with our techniques and propagate this set through the neural network. And then you can plug these tools together. And if you do this in a careful way, then this can work. So I just want to give one example. We start in this blue set here. There's one, you see one simulation here in black. And it's supposed to reach this green region here in the top left. And for the simulation, it works, but we don't know if it works for all the initial states. But if you use this technique, then you can actually prove that all the behavior eventually leads to this green set. So yeah. And the last slide is again a work in progress to do the same for, so there are actually many approaches now that try to do this for neural network controllers, but so far I haven't seen a single work for decision tree controllers. I guess there's not such a big hype about decision trees yet, or don't know. So a decision tree is just basically a binary tree where you have a condition on the inner nodes. For instance, v is less than 0, and then if the condition holds, then you go left, and if it doesn't hold, you go right. And then on the leaves, you have an action. In this case, it's about controlling this small car here. So you can steer it to the left or to the right. And this very simple tree would just say if the velocity in the forward direction, I think, is negative, then try to go left. And if it's so it will basically go up this hill on the left, and eventually gravity will pull it down. So then it will switch from going left here to going right, and then it will accelerate to the right, and then it will hopefully reach the goal. You can see here, this is the initial set that we started with. These are just simulations, and you can see that some of them actually reach the goal, but some others don't. So we would not be able to prove that all of these initial conditions lead to the goal state. So instead, we selected a small subset here. It's barely visible. But here you can actually see later that it branches out into a set. So yeah, this is work in progress, as I said. The problem here is mainly that for neural networks, you have these, I don't have that on the slide. For neural networks, you basically have a continuous output. So the neural network implements a continuous function, so it can give you slightly different floating point values for different inputs, whereas this tree gives you a discrete output, right? It can either say left or right, and this is very limited. So when you cross this decision boundary, when v switches from negative to positive, you have a very different behavior suddenly. So you need to be very careful with at these points where you cross the boundary. And the problem is, if you do this with sets, then part of your set will be on the left of the boundary and part of your set will be on the right. So to stay precise, you will need to split. And yeah, I find this very difficult to come up with a good algorithm that doesn't explode after a few steps. So yeah, let's see what we can do. Okay, so that's it. So I talked about reachability analysis, and I tried to convince you that this is useful in some cases when you want to really reason about all behaviors of a system. And I would say this technique is really mature now for linear systems. We can really analyze systems with thousands of dimensions in just a few seconds. For nonlinear systems and for hybrid systems, it's still quite hard. if you are lucky and your system has certain structure, then you can do something. But otherwise, I would say you can only hope to get a result in reasonable time for systems of moderate size. Definitely not hundreds of dimensions. And then we also saw these learned controllers that are coming up now, and these pose new challenges. There are some promising works going on. And I think my main takeaway from this work in this area is that you can do a lot if you exploit the structure of a system. If you just view it as a black box, you can do something, but you can usually get like something in the orders of magnitude faster if you look at the structure of the system and potentially even design a new algorithm for it. So all of these techniques are implemented in the open source tool JuliaReach, and now I'm happy to take questions and discuss. Thanks.
Thank you very much, Christian, for an insightful talk. Do you have any questions or comment for Christian in the audience?
I'm the most naive about these matters, but so for linear systems, you know what to do, everything's great. But the nonlinear systems, I guess what I'm interested in is not so much the linear versus nonlinear, but short-lived versus long-lived. Is that a reasonable interest on my part, or do you think that these systems are not well characterizable, or are they not sufficiently well characterizable that we could ever know long-term behaviors? Is that because the schemes numerically seem to fall apart after a certain time, no matter what you do? Is that not right?
I think so, yes. So where did I have that? I think this wrapping effect will eventually get you for nonlinear systems. I don't know any approach that can really avoid that in long term. If you really want to do that, I think these techniques are more promising, where you can prove. So if essentially you, maybe any example will do. So you can basically prove that you find some function, let's say a curve here. Can I draw here something like this? I don't know how you find them. Let's say you are a good guesser, and then you can prove that the blue set will always stay below this curve, and this is something you can do. But of course, again, this is I think this does not scale for very large systems, but I'm not an expert about these techniques. So I think if you really want long-term behavior, this is more what you want to do, unless you have a system that converges. So maybe something like this. If you can prove that actually this is not good, maybe this one. So if you can prove that you come back to the region that you have already been at, then you know that you close the circle basically, and you don't need to continue. So for such systems, these techniques are also good. But in general, if you have diverging behavior, then yeah.
Yeah, and certainly if you have, stochasticity could throw a wrench in everything, and of course chaotic dynamics would really be messing everything up. But what we do in the real world, of course, is throw in monitoring. So we don't know where it's going to go. When we launch a ballistic missile, we know that it's out of our control. But if it's guided missile, then we can cybernetically have that feedback and do a much better job about figuring out what's going to happen. So, is there a way to do that? Can you build in sort of this self-monitoring aspect into sort of the computational structures or the infrastructure that you've described, Is that part of the story? Can that be welded in? Can you do cybernetics in here as well?
Okay. I'm not sure if this is what you want, but of course you can run this analysis also on the fly, right, for a short time horizon, and then have an adaptive feedback controller based on what you predict will happen.
Right. And
Yeah.
so just doing a whole bunch of short-term simulations, basically.
Yes. I think I've seen this for a small quadrotor or something like that. This can work, yes.
Yeah, and that's all you need, right? It doesn't have to be any fancier than that. You don't have to build monitoring in structurally into a system. You just have to be willing to apply these methods. I guess they have to be computationally practicable so that you can do it. But you don't need any more infrastructure or architecture than that, you would argue.
Yes.
Okay, thanks.
But I have not done this myself, so I cannot give you any experience with that, but I know that people have done that.
Right. And I mean, some things may be, well, if it's a chaotic trajectory, then all bets are off. You know that you can't do very well in the long term. Okay, thanks.
Anyone else? Matthew?
I don't know very much about this, but does this generalize at all to stochastic systems? So I'm just looking at a book here that I haven't properly read, that has a section on fuzzy differential inclusions as an alternative to stochastic differential equations. And it kind of looks like you put bounds on how much the noise contributes at a point in time rather than knowing exactly what a sample path looks like. So,
yeah, so we often deal with noise in a completely non-deterministic way. So we completely ignore the distribution and we just say anything can happen. So this is of course very pessimistic, but then you can again deal with it in a rather nice way with these methods, but it will give you a crude overestimate if you really have let's say a non-uniform distribution. So for interesting distributions, I would say that there are specialized techniques, but it's I'm not sure that they work in this way. I mean, the way that I presented. Again, there are works for that, but I don't know them so well. I quickly showed this ongoing work with Ander and Scott, but here we do something that is more similar to what I showed before. We basically propagate this distribution inside the Taylor model, but other approaches, I think I think what we can do here is something that hasn't been done before in this way, particularly.
Thank you, Christian. Are there any other questions or comments for Christian? Okay. We've got some comments from Matthew on the chat if anyone's interested about the fuzzy differential inclusions. Thank you for sharing that. It's time. So thank you, Christian, for an interesting talk again. And hope to see you in Liverpool in the near future. And thank you everyone for attending and your contributions, and hope to see many of you in the next talk next week. Thank you very much.
Thanks.
Thanks, Christian.
Yeah, thanks again for the invitation.